Yeah, try and make this as much as possible a general video on information coding, but primarily it's about hashing, If you have seen any of my other videos, especially on recursion and recursive problem solving, I will quickly recap that idea. So the moment you are presented with a problem, you must remember two things. Every problem has a bound function, or also called a variant. And every solution has what is called as an invariant. A property in the solution, especially when it comes to coding of information, which must be maintained always. Like for instance, when we talked about error detection and correction, we were saying that you have an L dash width and you have to increase slightly if the error rate is say E. That means for every E bits you might anticipate 1 bit of error, then you might have to increase the size of the code by slightly so much so that all possible E or less flips do not result in the same value. That is, even though this information that you're sending is altered by at most E bits, E or less, yet if those E bits result, as you can see, you can always do that. You can try it out with 8 bits and all that. There are many other ways of doing it as well, and also to introduce a fair bit of redundancy in the information so that the probability of error decreases. So in this case, that becomes the invariant. Now, this is just to illustrate the power of this technique. Initially, when I tried doing it, I never succeeded, but it's actually very true. Most of us, for instance, when we have to code an information of length 2 power L dash, this is with regard to data compression and hashing, in L bits, L dash bits in L bits, mapping is from M to S. Then naturally, if we take the ratio of M by S, it will turn out to be D, say some value D, and it will usually be large. For instance, if you want to code 256 bytes in 8 bytes, then nearly 32 times it becomes. So it will be very, very large. Actually, you can actually code quite a lot of information in 8 bytes, but we also observe that square root of M by square root of S is equal to square root of D. In other words, if you have 256 bytes by 8 is equal to 32, 16 by root 8 will be nearly equal to square root of 32. 2 power 5 by 2. As you can see, it drastically reduces. So if you have a large piece of information, you're always aware you wish to code in a smaller piece of information. The idea of coding the former half in this half and the latter half in this half always occurs to us. But what we find is order is never preserved in that case, right? So you can, to overcome that, you can very easily overcome that as follows. Let M equal to M1 square plus m naught, and s equal to s1 square plus s naught. Okay, so in other words, we are taking square root of m. We can define the hash function h of k comma s, where k is a key which is less than m, or less than or equal to m minus 1. That is 2 power l dash, different values there. It's less than 2 power l dash. Okay, so we can define, so we express the key simply as, break it up into two parts. K is equal to k1 square plus k naught, and we define the hash function as h of k comma s is equal to h1 of k1 into s naught. I shall write it in the below here. It can be defined as recursively as h1 of k1 times s naught plus h naught of k naught comma s naught comma s1. That is, we first perform, it's a bit like that Horner scheme for evaluating a polynomial. First you take the lower part k naught and hash it to s naught, which is order preserving. Then you compose that ordered part with the larger part of the key, and then for the hash that two together into s1, or you can hash it actually to s itself. It should not be s1, sorry, it should be s. So this way you can keep composing it and hashing it. Now these different families h0, h1, h2 will depend on, if you divide it into p parts, number of parts you divide it into more, then you can find some generic or general way in which, depending on a function, general way of defining hi as a family of functions which satisfy a certain property, right? Because if you know, you take a binary string or whatever it is of a certain value, those which key values always behave in a particular manner only, it's probabilistic. Which is a recursive normal kind of a distribution. So it's all, you can always define a hash function this way. Similarly also, you can also try other ways of doing it, but you can improve upon that based on for instance, if we have to map say 2 power l dash to l to 2 power l, then we could, the general, again we determine r such that r power l dash equal to 2 power. This is something that we already know. So therefore gives you r equal to 2 power l by l dash. Right? So this could be the strategy adopted. That means you have to recursively map r power I plus 1 minus r power I to 2 power I plus 1 minus 2 power I. This will also preserve the order. So hash value will be, if you map this to this, you find out the leftmost one in the key, right? And that will be the value for I. So the next next bit value will be I plus 1. So you take the key from the ith and to this, then you map this recursively into r power I plus 1 minus r power I. And the hash value is computed as r power I plus h of k dash, comma, r power I plus 1 minus r power I. This can be done recursively, but what you will notice here is that r power I behaves in a certain manner, but if you take r power I, if you take a normal distribution, what happens is it's very symmetric, because NCR is equal to NCN minus R. It's always symmetric, right? Only if the value of R is true is the symmetry preserved. If the value of R happens to be less than 2, that means for much larger values, even though they have a behavior similar to, that means for the other half, that is r power L dash minus 1 minus r power L dash will be less than 2 power L dash minus 1 minus 2, will be less than summation of all of those r power I less than L dash minus 1. So, right? Because this property of equality will not hold good because r has become small. So what you can do to compensate for the fact that even though larger numbers do come, it will have a behavior slightly not desirable because of this properties. We have decreased the value of r to less than 2. So what you can do is, you can break up to some extent, you can try and break it up till you come to a small value for that. And then you can try to a reasonable, say if you have take a 64-bit value up to 32 times, you can try and say, or say 32 times or 48 times till you come to a 16-bit value. Then you can just simply directly apply that and hope for the tail end behavior to whatever. For the other part it will be similar, or you can take half of it. This is with regard to hashing alone. For information coding, but there is also another idea that is worth considering, that is very useful, especially if you are looking for defining a hash function for hash table management, ordered storing of keys in an ordered hash table. Now if you take any two numbers m by n, we know from the division algorithm, we know m is equal to, there exists quotient and a remainder such that m is equal to q times n plus r, where 0 less than equal to r less than n. Okay? Now what you might have observed is the remainder does not change if the value of the remainder, right? This is symmetry, right? If you say m by n is roughly equal to q, then m by q is roughly equal to n. Now n happens to be constant all the time, right? But for different values of the remainder. What you will observe here is the minimum of, if r less than minimum of q comma n, then the value of the r is the same irrespective of whether you divide by n or irrespective of whether you divide by q. In other words, that remains constant always, right? This is only for numerical hashing. You may try to extend it or improve it for other longer stuff, but for hash table management. So what happens is, if you have, say, the value of m is equal to a into d, right? A is the quotient part and d is the divisor, and s, so therefore m by you have some value s close to d, nearly equal to d, it won't be exactly d, right? So what happens is, you can always try to right? So you'll have r different values here and some quotient you will get for a given key, right? Now if you have some value for a given key, if you have a quotient, a divisor and a remainder there, but the multiplication factor for the quotient for the hash table should be c, which is much smaller than d, right? So you just do d by a, right? So you can take some value for small value for a slightly less than a, so say 2 by a by c, so, or a by 2 should be fairly, because usually between, so 2d by a, right, is equal to this. So now what should the value of c itself be? If you take some value c, right, for all values of r that is less than q, the remainder will remain the same. So if you divide d by, say, this value, we call it as e. If we divide d by e, we will get a value x, right? This means we can control disorder or controlled chaos. We can have ordered hashing by controlled disordered hashing, right? How do we do that? That means if we fix the number of collisions, that is d by a is fixed, right? But this value c, we have to slightly increase it, that is to more than q, the value of more than a, to a small extent, so that from that if we select exactly, there are exactly d different a subsets of a plus some value x. That can be easily computed. I shall take this more detail in another thing. The same idea can be applied for error detection and correction as well as for information coding as well. So these kind of ideas you can come up with, and other than this also you can also come up with many other ideas, so that the number of, you can have fair amount of redundancy and at the same time very little necessity for expanding the length of the code. Okay, so another idea you could come up with is, for instance, like I said, one was selection, right? If you select 8 bits out of this, all possible 8 selections, 8 bits, they each of those, you need not select all possible. In fact, all you can do is you can make an improvement to that design by, if you have, say, n bits here this way, You start off by selecting some small value, number of bits, find out what its value, keep a table here. Right? So one you might have to keep up transition, or the other you might have to keep it down. So what you can do is you can take this. If this comes up to, say, you take 8 bits here, it will come up to a table of size 256. The first 8 bits match to that. Okay? So you keep a count of the number of times this has occurred. Now if you just shift this and take the next 8 bits, only two possibilities arise. It either goes up or it goes down. Right? If it goes down, that means all the because it only differs by 1 bit. If you know this has occurred, the next thing that can occur, if you take the next thing, shift by 1 and 8 bits, can be only one of two values in this table. So you keep a count of, say, if you just keep up only, it also is sufficient, because the up of the other, this thing will actually point to this only. So you can get the down of this. Or like that. So if you keep this kind of a table here, right, you can take for the probability that two pieces of information match to this will be virtually 0 only. If you take the length of this to be fair enough for a given length of the information, L dash by L is fair enough, you should get, the size of this table will be very, very small. You can use this both for data compression if you are able to figure out quickly how fast to recover, and it can be used both for error detection and correction as well as for data compression, these kinds of methods. So simultaneously you will find that if you try to do one of these, you will end up doing the other. In an earlier video I had made a video on checksum hashing, which was checksum hashing part 3. It is not very clear. I should define the hash function here again. If you can divide the k into p parts such that k is equal to k p minus 1 power p minus 1 plus k p minus 2 power p minus 2 plus and so on up to k naught, or plus k1 square plus k naught. And the hash function or checksum hash function is defined as h of k is equal to there will exist constant C0, C1, C2 for a particular ideal base B such that base B and constant C0, C1 and up to C minus 1 such that h of k is equal to Cp minus 1 log of k p minus 1 to the base b whole power p plus C p minus 2 log of k p minus 2 whole power p minus 1 and so on, plus C1, this is also to the base b, log to the base b of k1 , the whole square plus C naught log to the base b of K naught is fairly unique and also order preserving. So you can get a checksum which is order preserving and data compressing, and also probably for error detection and correction and so on. So you can do all of that in one shot.